How do you visualize 3D transformations in robot kinematics? Imagine trying to see how a robot moves in space without actually watching it. Visualizing 3D transformations helps us understand how each part of the robot shifts and turns. It's like giving the robot a set of eyes to see where it is and where it's going. In robot kinematics, we use mathematical tools called transformation matrices to do this. These matrices combine rotation and translation, which means they tell us how a robot link rotates and moves in space. Think of each link as having its own coordinate frame, like a tiny set of axes attached to it. These axes are usually labeled as X, Y, and Z, with the Z-axis pointing along the joint's movement direction. To visualize the robot's position, we assign coordinate frames to each joint and link following a standard method called Denavit-Hartenberg parameters. This method makes it easier to keep track of each frame's position and orientation. The core tool here is the homogeneous transformation matrix, a 4x4 matrix that combines a 3x3 rotation matrix and a 3x1 translation vector. The rotation matrix shows how the link is oriented relative to the previous frame, while the translation vector shows how for it is from the previous link. When we multiply these matrices from the base of the robot to the end-effector, we get the overall position and orientation of the robot's hand or tool. This process is called forward kinematics. To see this in action, engineers often use computer software or simulation programs that graphically display the robot's links and joints. These tools show how changing joint angles or displacements affects the robot's pose in three-dimensional space. Color-coded axes, like red for X, green for Y, and blue for Z, help us quickly understand directions and rotations. Interactive scripts written in programming languages like Python can also dynamically calculate and display these transformations. They let us see how each joint's movement changes the robot's position in real time. Visualizing these transformations is essential in electrical engineering because it helps design control systems, interpret sensor data, and plan robot motions. It allows engineers to verify that the robot moves correctly and that signals sent to motors produce the desired movements. In summary, assigning coordinate frames, using transformation matrices, and combining these matrices step by step help us see exactly how a robot moves through space. This visualization makes it easier to control and troubleshoot robotic systems, ensuring they perform accurately and efficiently.